Have you ever stopped and just wondered about the sheer magic that's happening inside your computer every single second? I'm talking about real magic. How it can run a dozen different apps, a browser with 50 tabs open, a massive game, your code editor, all at the same time, and it doesn't even break a sweat. It feels like it has an infinite amount of memory. But does it? I mean, really think about that for a second. How is it even possible to run something like a huge video editing program or a complex simulation that is physically bigger than all the RAM you have in your machine? It just seems impossible, right? It's like trying to pour 2 gallons of water into a 1-gallon bucket. And yet, your computer pulls off this little miracle all the time. This isn't just some clever party trick. It's a fundamental illusion that makes all of modern computing even work.
So how does it do it? Well, the secret to this paradox is hidden deep inside the operating system and one of its most important jobs: managing memory. The stuff we're about to get into is, and I'm not kidding, the bedrock that supports literally everything you do on your computer. So today, let's open up the book and really deeply understand Chapter 8, Main Memory.
To really get how this magic trick works, we've got to build it from the ground up. We're going to start with the main problem, this idea of address translation. Then, we'll take a little trip back in time to look at the first simple ways they tried to solve this, and a huge problem they ran into called fragmentation. After that, we'll check out 2 really powerful ideas, segmentation and paging, that tried to fix things. We'll dive deep into the maps of the system, the page tables, and then finally, we'll see how the processors you actually use, Intel, ARM, put all this theory into action.
Okay, let's dive right in. At the very heart of all this memory management stuff is one central problem. See, the CPU, the brain of the whole operation, it lives in its own little world. It generates addresses for code and data, and it just assumes it has this beautiful, clean, private memory space all to itself. But the physical RAM, the actual memory chips, that's a chaotic, shared space. You've got tons of different programs loaded all over the place. So the whole challenge is, how do we bridge the gap between the CPU's perfect illusion and memory's messy reality? To figure this out, we need 2 key terms: logical address and physical address. A logical address is what the CPU creates. Think of it like a package's tracking number. That number, it stays the same for the whole journey. From your program's point of view, its data is always at, say, address 100. A physical address, on the other hand, is the actual spot on the RAM chips. This is like the exact shelf in a specific aisle in a warehouse where your package is sitting right now. That physical location can change, but the tracking number never does. The OS's job is to translate that consistent logical address into whatever the current physical address happens to be.
Now, you might be thinking, okay, the OS does the translation, but if the operating system software had to jump in and do this for every single time your computer accessed memory, for every instruction, every variable, your computer would slow to a crawl. It would be unusable. The process has to be basically instantaneous. And that's why we have a special piece of hardware to do the job, the Memory Management Unit, or MMU. It's a chip that sits right between the CPU and your RAM, and its entire job is to do this address translation at lightning speed. It's the system's official super-fast interpreter.
So how's this little interpreter work? Well, in the simplest version, it uses 2 special numbers it keeps in registers, a base and a limit. Let's walk through it. Step 1. The CPU says, I want to access logical address 100. Step 2. The MMU checks if that's a legal request. Let's say your program is 5,000 bytes long. The OS sets the limit register to 5,000. So the MMU checks, is 100 less than the limit of 5,000? Yep, we're good to go. Step 3. Now we figure out the real address. Maybe your program got loaded into memory starting at physical location 10,000. The OS sets the base register to 10,000. The MMU just does simple addition. 10,000 plus 100 is 10,100. That's our physical address, which you see in Step 4. But this also gives us protection. That's Step 5. What if the program tries to access address 6,000? Well, the MMU checks the limit and sees that 6,000 is not less than 5,000. That's illegal. The MMU immediately blocks it and sends an alarm, a trap, to the OS, which will probably just terminate the misbehaving program. So this simple little system does both translation and protection. So that base and limit idea works perfectly for one program. But the whole point of an OS is to run lots of programs at once. The very first attempt to do this was pretty simple and intuitive, but oh boy, it introduced a massive system-killing problem called fragmentation. This early idea was called contiguous memory allocation, And it's exactly what it sounds like. Every program that starts up gets one single unbroken block of memory. Think of your computer's memory as one long parking lane on a street. When a new car, a new process, shows up, the OS has to find a single empty spot that's big enough for that car and park it there. Simple, right? But what happens when cars of all different sizes keep arriving and leaving all day long? Well, the OS has to be a parking attendant, right? It needs a strategy for finding an empty spot or a hole in memory. There are 3 classic ways to do this. First fit is the lazy attendant. Just drive down the street and take the very first spot you find that's big enough. It's fast, but you might leave a little tiny, useless bit of space. Then you have best fit. This is the super meticulous attendant. He measures every single empty spot to find the one that fits the car the most perfectly. The idea is to waste as little space as possible. And then there's worst fit, which sounds kind of crazy. It finds the biggest available spot. The thinking here is that if you take a small chunk out of a huge spot, the leftover piece will still be nice and big and useful for another car later. 3 different strategies, but they all lead to the same disaster. No matter which strategy you pick, you slam into this problem of fragmentation, just wasted space. And it comes in 2 flavors. On the left, you've got the real killer, external fragmentation. This is our parking lot nightmare. After cars come and go all day, you end up with lots of tiny, empty spots between all the parked cars. If you add up all those little empty spots, you have plenty of room for a big truck, but because none of the individual spots are big enough, the truck can't park. Your memory has shattered into useless little pieces. Then on the right, you have internal fragmentation. This happens when you give a process a block of memory that's just a little bit bigger than it needs. Maybe memory chunks come in sizes of 8, but you only need 7. That one leftover byte is wasted inside the process's allocated space. It's not great, but you can live with it. But external fragmentation, that was the fatal flaw that made this whole approach a dead end. See, the problem with that old method was it treated a program like one giant blob of stuff. But that's not how we, as programmers, think about our programs at all. So the next step in the evolution of memory management was something called segmentation, and it tried to create a memory model that actually matches how we structure our code.
I mean, think about how you write code, right? You don't just write one giant continuous file. You have these logical, distinct pieces. You've got your main program code, a bunch of functions, a place for your global variables, the stack for local variables, the heap for when you malloc stuff, and maybe you link in a math library. Each of these is a different component with a different job and a different size. Segmentation says, hey, let's honor that. It lets the OS treat each of these logical units as its own separate, variable-sized segment.
So how does this work? A logical address isn't just one number anymore. Now it's a pair, a segment number and an offset inside that segment. Think of it like a library reference. Operating Systems textbook, page 365. So the MMU uses a special segment table for each program. When the CPU asks for an address, the MMU takes the segment number, our textbook title, and uses it to look up the right entry in this table. That entry tells it 2 things: the physical base address where that segment starts in RAM, and its limit, or how long it is. Just like before, it checks if the offset, our page number, is within the limit to make sure we're not going out of bounds. If it is, it just calculates the physical address, base plus offset. This is a way more logical way of looking at memory. But do you see the problem? Because all the segments are different sizes, the code segment is huge, the stack is small, we're right back at the parking lot problem. We're still trying to fit different sized cars into the memory lane, and we're going to end up with those same useless tiny holes. We've made the model more elegant, but we have not solved external fragmentation. Not yet.
So, segmentation was a beautiful idea, but it didn't fix the biggest headache of all, fragmentation. To really solve it, computer scientists had to do something radical. They had to throw out one of the most basic assumptions they'd been working with, the idea that a program's memory has to be all in one piece. The solution they came up with is called paging, and it is without a doubt the single most important memory management technique used in pretty much every modern computer.
The big idea behind paging is brilliantly simple. First, we take a program's logical memory and we chop it up into small, fixed-size blocks called pages. Just imagine tearing a book apart into all its individual pages. Second, we take our physical memory, the actual RAM, and we chop it up into fixed-size blocks of the exact same size, and we call those frames. Think of these like the empty slots in a 3-ring binder. Now here's the magic. Any page from our program can be put into any available frame in memory. Page 1 can go in frame 5, page 2 can go in frame 27, and page 3 can go in frame 2. They don't have to be next to each other at all.
So now, the logical address from the CPU is seen as 2 parts: a page number, which tells us which page of the book we want, and a page offset, which tells us which specific word we want on that page. The translation is pretty straightforward. The MMU grabs the page number and uses it to look up an entry in a special map called the page table. The page table is just a simple lookup. For every page in the program, it stores which frame in physical memory that page is currently sitting in. So the MMU gets the frame number from the table, sticks the page offset onto the end of it, and boom, it has the final physical address. This totally solves external fragmentation. Because every page and every frame is the same size, there are no weirdly sized holes anymore. Any empty frame can hold any page. It's a perfect fit every time.
But wait a second. Let this sink in for a minute. We've just created a huge new problem. If that page table, that map, is stored in main memory, then what happens every time we want to get a single piece of data? Well, first, we have to go to memory to look at the page table to find out where the data is. That's one memory access. Then, we have to go to memory a second time to actually get the data. We call this the two-memory access problem, and it would literally cut the speed of your computer in half. That is just completely unacceptable. No one would ever use that.
The solution to this speed problem is, you guessed it, another piece of special hardware. It's called the Translation Look-Aside Buffer, or TLB. The TLB is basically a tiny, super-fast cache that's built right into the MMU. And all it does is store the most recently used page-to-frame translations. It's like having a sticky note on your monitor with the phone numbers of the 5 people you call all the time. Instead of looking in the huge phone book, the page table in memory, every time, you just glance at the sticky note first. So when the CPU generates an address, the MMU checks the TLB first. If the translation is there, we call that a TLB hit, it's almost instantaneous. If it's not there, a TLB miss, then okay, we have to do the slow lookup from memory, but then we add that new translation to the TLB for next time. And because programs tend to work in the same small area of memory for a while, this works incredibly well. The TLB usually has a hit rate of over 99%, which makes paging fast enough to actually use.
Okay, so paging solved fragmentation. The TLBs solved the speed problem. But in slaying those two dragons, we've accidentally created a new monster. Modern computers can address huge amounts of memory. So what happens when the page table itself, the map we need to find our way around, becomes too big to even handle? What if your map is bigger than the entire country you're trying to explore?
Let's put some numbers on this, because it's kind of shocking. Take a normal 32-bit system. The most memory it can use is 4 gigabytes. Now, if we use a pretty standard page size, like 4 kilobytes, how many pages could a program possibly have? Well, 4 gigabytes divided by 4 kilobytes is a little over 1 million pages. Okay, a million entries in our map. If each entry takes, say, 4 bytes to store the frame number, then the total size of the page table for a single program is 1 million times 4 bytes, which is 4 megabytes. You can't just set aside a 4 megabyte chunk of precious RAM for every single little program that's running. That would be an absolutely insane waste of memory. The map itself is too big.
The solution here is so clever it's a little bit mind-bending. It's called hierarchical paging, and the idea is just nuts. If the page table is too big, well, we just use paging on the page table itself. We page the page table. Let's trace it out. In a two-level system, we split the page number part of the address into 2 pieces, an outer index and an inner index. The outer index, P1, is used to look into an outer page table. But the entry we find there doesn't point to our data. No, it points to the physical address of another second-level page table. We then use the inner index, P2, to look up the entry in that table. That entry finally gives us the frame number for our actual data. Now, why on earth would we do this? It sounds way more complicated. But here's the brilliant part. We only need to create those second-level page tables for the parts of memory the program is actually using. If a program only uses a little bit of memory at the beginning and a little bit at the end, we don't need to create or store any of the page tables for that huge empty space in the middle. This one trick saves a phenomenal amount of memory.
All right, so we've built this complete theoretical model for modern memory management. It's robust, it's clever, but is this how it actually works inside the silicon in your computer? Let's take a quick look at how real-world processors from companies like Intel actually implement these exact ideas.
So let's see how this all comes together. Intel's classic 32-bit architecture did something really fascinating. They took a hybrid approach. They didn't want to give up on the programmer-friendly model of segmentation, but they absolutely needed the efficiency of paging to get rid of fragmentation. So they just did both. A logical address first goes to a segmentation unit, which translates it to an intermediate address called a linear address.
Then, that linear address is fed into the paging unit, which uses a two-level page table, just like we talked about, to get the final physical address. It's a classic engineering trade-off. You get the best of both worlds. You get the logical separation and protection from segmentation, and you get the memory efficiency from paging. And that brings us right back to the beginning. This entire journey, from those simple registers all the way to complex multi-level paging, it's all done to create one grand illusion, giving every program its own private massive memory space, even though it's all running on shared, limited physical RAM. This is how you run that 20 GB program on your 16 GB laptop. Now, there's another layer called virtual memory, where the OS can even move pages to your hard drive, but the core engine that makes it all possible is paging. So I'll leave you with this. What's one thing you do on your computer every single day that you now realize completely depends on this invisible, complex dance between logical pages and physical frames?